We can do the same thing with water. So water's got a Lewis structure that looks something like that. And if we count the number of repulsions to apply VSEPR, every lone pair, every bond counts as a single repulsion. So we've got 4 repulsions there. So that suggests that we've got that tetrahedral arrangement of electrons. And we can put our atoms anywhere we like, and we can put our lone pairs anywhere we like. Is really not a problem there. I like to put the atoms on these ones here because these are the flat in the page ones. I just think it's easier to see. There's nothing wrong with putting them there if you want to. I just think it looks more untidy. So this would be the VSEPR geometry. So I should go ahead and write this is Lewis up here, and this is VSEPR down here. Remember, the wedges are the ones coming out, and the dashes are the ones coming in, and the lines are flat on the page. What would the angle be? Well, it would expect it to be 109 degrees if it was perfectly tetrahedral. But the reason that it deviates from that is that those lone pairs are actually kind of large, and there's 2 lone pairs, and so each one of these lone pairs kind of squeezes down this angle, and it squeezes it down to considerably less than 109.5 degrees. In fact, in water, it's 104.5 degrees, and I think that that's kind of an interesting angle to remember. So water has that shape there. Now, what about the geometry? Again, the electron geometry, where the electrons are, is still tetrahedral. So all of these 4 repulsions are always tetrahedral, but the molecular geometry, or just the geometry for short, is bent. And so you've got those atoms, they're not in a straight line, so I can draw kind of that structure there if I want to. And since all 3 of them aren't in a straight line, if they were, they'd be called linear, but because they're not, we call that geometry bent. So that would be the full answer to the geometry of water. All right, so how about a couple of practice geometries? So how about something like the nitrite ion, NO2 minus, and how about something like, oh gosh, what would be a good one? Maybe the phosphate ion, PO43 minus. So you should be able to draw Lewis structures, and from that draw 3-dimensional geometries, and you should be able to give them both electron geometries and molecular geometry. So pause the video, have a go, and let's compare notes. All right, I'm back. So let me go ahead and start by drawing the Lewis structures for both of these, if I can spell Lewis, and the Lewis structure for NO2. And again, I'm not going to go through how to draw these Lewis structures at this point. We've done that in some previous videos, but I'm just going to quickly sketch this out. And it's an ion, so I guess I should probably go ahead and put the charge. Oh, wait a minute. We only need 1 charge there. So the charge should go up to the top. And phosphate, if we draw phosphate, let's see, it is PO4. All right, 1, 2, 3, 4. And we want to complete the octets around those outer atoms. Oh, what a pain, what a pain, what a pain. There we go. And the whole thing has a 3 minus charge. So those would be the Lewis structures. Now, in both of these, right, if we want to convert to VSEPR, we have to count repulsions. So around nitrite, we've got a lone pair, we've got a single bond, and we've got a double bond. Remember, any kind of bond counts as a repulsion. And around phosphate, we've got a bond, a bond, a bond, and a bond. And remember, we're looking around that central atom. So now we can go ahead and we can remember in VSEPR terms, right, those repulsions, if you've got 3 of them, would give you that trigonal planar. So I've got my N and I've got my trigonal planar. So that is that sort of 120 degree kind of arrangement. And they're planar, that means they're flat. So I've got a lone pair on the top. I got a bond to oxygen on the bottom right, and I got a bond to oxygen on the lower left, and I guess it's a double bond, so I could write it something like that. So I think that would be totally fine there for the VSEPR geometry. Okay, at least that's the shape. Now, what is the name of that geometry? Well, don't forget, right, the name of the geometry is where the atoms are. So the atoms are in this bent shape here, right? So the geometry we would call bent. Now, the electron geometry is trigonal planar because the electrons, you got a lone pair, a double bond, and a single bond. They're trigonal planar, but the molecular geometry is where the atoms are. And when we ask for the geometry, that's almost always what we want. Now, in the case of phosphate, I believe the electron and the molecular geometry is identical because if you've got 4 repulsions, then they take that tetrahedral geometry. So remember, the lines for the ones that are in the plane, the wedge for the ones coming out, the dashes for the ones going behind, and it's going to look something like that. That angle is going to be, all of them are going to be 109.5 degrees, and the name of that geometry is tetrahedral. And I suppose one last thing I should comment upon is since you've got that lone pair on nitrite that's kind of large, it would be expected to push down and contract those angles a little bit. We would probably expect that angle to be a little bit less than 120 degrees. So that would be the end of that problem. Well done.